Okay, so welcome back. We are doing section 6.3, which is called Similar Triangles and Other Figures. And we're going to be solidifying understanding, which means we're still exploring a couple of ideas, and then we'll move to practicing. So today you'll be able to determine criteria for triangle similarity. What that means is what what do you need in order to say that these two triangles are similar? Okay. And what's the difference between common usage of the word similar? Rectangles are more similar to each other than rectangles and triangles are. And the mathematical conventions for the word. What does it mean for two polygons to be similar? And how can I prove or disprove that two triangles are similar? So this word similar under the mathematical idea is relates to the idea of similar outside of no of math, but it's not exactly the same. Okay. So two figures are said to be congruent if the second one can be obtained from the first one by a sequence of rotations, reflections, and translations. So what that means is if I wanted to know if these two pieces of paper are the same size, what would you do in real life? You would take them, stack them, and then you would kind of tap them on the desk to make sure that they all lined up. And then you would measure them with your eyes, right? You would see, oh yeah, all the corners match up. So that's no different than in math. So if I took the two pieces of papers, maybe I reflected it or rotated it so that they lined up, and then they moved them together. So I translated them. So I moved them together. So it says previously we found that we only needed three pieces of information to guarantee that two triangles were congruent. For example, SSS, ASA, or SAS. But what about AAA? Are two triangles congruent if, give me 1 second. So what about AAA? Are they going to be congruent? So that's what we're going to wonder about today. And in this task, we'll consider what is true about triangles that are similar and not congruent. The definition of similarity is two figures are similar if the second one can be obtained from the first by a series of rotations, reflections, translations, and dilations. Now if you look at the difference between congruent and similar, they just added dilations. And remember, dilation is like if you have your phone and you pinch to zoom out, or you spread out to bring it and to zoom in. Okay. So obviously if you zoom into something, those two things aren't going to be congruent because now one's bigger than the other. And so that's what a dilation is. So Mason and Mia are testing out conjectures about similar polygons. Here is a list of their conjectures. So number one, all rectangles are similar. All equilateral triangles are similar. All isosceles triangles are similar. All rhombuses are similar, and all squares are similar. So which of those do you agree with? Which of these conjectures do you think are true? Do you think all rectangles are similar? Remember, our definition of similar is two figures if they can be obtained by rotations, reflections, translations, or dilations, right? Okay, so go ahead and tell me which ones you think are true. Mason is explaining to Mia why he thinks conjecture 1 is true using the diagram. So here's his two diagrams, why these two are similar. Okay, he says all rectangles have 4 right angles, check. I can translate and rotate ABCD until vertex A coincides with Q. So he's going to put this one on top of this one, right? Since A and Q are both right angles, we see side AB will lie on top of QR, and side AD will lie on top of QT. So here, so there he's basically saying we're lining up this on this side and this on this side, right? Excuse me. I can then dilate the rectangle ABCD with point A as the center of dilation until B, C, and D coincide. So he's going to zoom in, just like right now. I don't know if you guys can tell, but I'm going to zoom in. This is me zooming in because I'm not unpinching, but spreading my fingers apart. Or I'm going to pinch my fingers so that they zoom out. So do you agree with Mason? Do you agree with Mason? Okay. So here's the question. Does Mason's explanation convince you that the rectangle ABCD is similar to rectangle QRST based on the definition of similarity above? Does his explanation convince you that all rectangles are similar? Why or why not? So some of you are saying, Ms. Johnson, but this is a square. I want to remind you that all squares are rectangles. Okay, every single square. The definition of a rectangle is 4 right angles. That's exactly what a square has. A square has a couple more pieces in the definition, like all 4 sides have to be equal, right? So, do you agree with Mason's definition? Like if I line these 2 corners up and I'm going to just zoom in on this one, can I ever make ABCD line up with QRST? And so what do you think? Yes or no? So most of you can see that these 2 are not similar, right? And the reason why is however much I have to make side AB grow so that it lines up with R, so that B lines up to R, is not going to be the same as AD so that it matches with QT, right? So based on that, that tells me that first conjecture is not true because these 2 rectangles are not similar. Okay, moving on. So Mia is explaining why she thinks conjecture 2 is true. Okay, so if you forgot what conjecture 2 is, I kind of did. It says all equilateral triangles are similar. Okay, so she says all equilateral triangles have to have 60-degree angles. Okay, so she's marking off the 2 criteria, right? The criteria for similarity, and I'll highlight these here, is number 1, they have to be able to rotate, reflect, translate, and dilate. Okay. So number 1, she says all equilateral triangles have 3 60-degree angles. So then she's saying this is congruent to this, congruent to this, congruent to this, congruent to this, congruent to this. And so far that's good. And she says I can translate and rotate ABC until the vertex A coincides on Q. So here's A coinciding on Q. And since A and Q are both 60-degree angles, they'll lie on top of side QR and side AC. So this side, oops, I wanted to change colors. This side here, QR, oops, AC will be on top of QS. And AB will be on top of QR, right? So do you see how you're doing that? And then she says, then I can dilate ABC with point A as the center of dilation until B and C coincide with point R and S. So I want these 2 to grow, C to grow all the way till it gets to S, same with R, okay? And if you want, we could use like kind of like tracing paper and like look at this so that you all can see that these 2 are in fact the same, right? So do you agree with Mia? Do you agree with Mia? Okay. And so in Mia's argument, the scale factor for the dilation matches from B to R. So as this one grows, so maybe it looks kind of like, I don't know, something like this, where ABC is right there, right? And then you're going to zoom in, you're going to go like this to ABC until ABC kind of like puts itself onto QR, right? So kind of like if I don't know if I could do this. Let's see if I could do this right. if I could take this and stretch it and then let it go on top of like that, kind of. Do you see how that kind of is what I was trying to talk about? And notice whenever you're doing this kind of similarity, I'd have to scale it by the corners like this. And I'm dragging the corner, not like this by the left side or the right side, right? So hopefully you see how those line up, and that helps you understand what I'm trying to get. So here it went from here, and then I'm making this grow, right? I'm pushing this out. I'm zooming. I'm dilating this until they line up there. Does that make sense? So I'm like stretching it out like evenly. Okay, let's move on. Number 4, for each of the other 3 conjectures, write an argument like Mason's and Mia's to convince someone that the conjectures are true or false. So all isosceles triangles are similar. Do you think that's true? Do you think that's true? Basically, if I drew you an isosceles triangle and maybe someone draws this one that looks like this, and I drew another isosceles triangle, would they have to be similar? Would I be able to zoom in, rotate, translate that until we got it? And so some of you are thinking, do all isosceles triangles look like this? Or smaller or bigger versions of this, right? And the answer is no, because here's one and then here's another, right? Okay, so this is going to be a no. Are all rhombuses similar? Are all rhombuses similar? Okay. And so again, if you don't remember what a rhombus is a 4-sided figure where all sides are congruent, like this. So can I draw another quadrilateral that has 4 sides that are congruent that doesn't look like this, whether I grow it or make it little or big? And the answer is no. Because look at, here's one and then here's a square. No matter what I do, I can't get this one to be on top of this one and be the same. Even if these lengths are the same here, right? Because these angles aren't. What about this one? All squares are similar. So the definition of a square is that it has 4 congruent sides and 4 congruent angles. So there's a square, and then maybe I draw a smaller square. Do you think these have to be similar? Can I grow this smaller one so that it's the same size as that bigger one? And the answer is yes, right? And so therefore I can dilate this. So if I go like this, A, B, C, D, E, F, G, H, if I can take G and put it on top of D, and because all of those angles are right angles, this side here would line up with this side here, right? And this side here would line up with this side here, right? And then you would just grow it. And because it's growing by the same scale factor, you should be good. Okay. So Mason has another conjecture. He said scaled drawings of polygons are similar figures. Scaled drawings of polygons are similar figures. So what a scaled drawing is, it's a smaller version of the same thing. So if you remember when we were making that copy of the of that man, remember from the first or second lesson, this is what we're doing here. That's a scaled drawing. So here's what Mason knows about scaled drawings from previous work. Corresponding angles of scaled drawings are congruent and corresponding sides are proportional. So Mia proposes that they try to justify this conjecture for scale drawings of triangles. She suggests the following diagram. So here's the diagram that she's talking about, okay? I'm going to read it to you. So explain how you can use the definition of similar figures. Two figures are similar if the second can be obtained by the first by a sequence of rotations, reflections, translations, and dilations to show the following drawings of triangles are similar. So the very first thing, so you're given that the corresponding angles are congruent and the corresponding sides are by a factor of k. So can you see how if I took this one, rotated it just a little bit so that this side would match up with this side, right? And then I dilated this side, so maybe like B was here, something like this. Maybe B is here, and then you take it. Oops. So then you take this, right? And then you line it up. So you translate it. I did a pretty good job of the drawing. And then I dilate it, meaning I stretch it out. And do you see how they match up? Right? That's what I'm looking for. And so the answer here is yes. You can translate A so that it sits on top of R. And since the angles are congruent, this guy here, remember I had him here. So this guy here, I will call him C prime. And this is going to be B prime. When I line them up like this, that's that triangle, right? So it's like I took this triangle, I rotated it a little bit, and now he's here. So then I'm going to dilate this triangle until he's the same size as this. And so that is going to be true. So the next one says, how can you extend Meehan and Mason's justification for scale drawings of triangles to the similar? And so again, you're given the fact that all the angles match up, they're corresponding and they're congruent. So this little angle is congruent to this one. The next angle is congruent to the next angle. This one's congruent to the next one. And the last one's congruent to the next one. And they're proportional because this is A to KA. This is D to KD. C to KC, and B to KB. So notice that it grew by a factor of K, right? That's what they mean by scale factor of K. Okay, so then it says, while the definition of similarity given at the beginning of the tasks was for similar figures, including figures that have nonlinear boundaries, an alternative definition or similarity can be given for polygons. Two polygons are similar if all corresponding angles are congruent. So I'm going to highlight some parts here. If the corresponding angles are congruent and the corresponding sides are proportional. So we've got congruent angles. Sorry, let's go. Congruent angle, 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 congruent angle. So this one right here, that's checked. And then they're proportional. So proportional means if I go from here to here, I'm multiplying by K. Now, if I go from here to here, I'm still multiplying by K. And from C to KC, I'm still multiplying by K. And from B to KB, I'm still multiplying by K. So that is what we call proportional. Proportional check. Okay? So if this was being multiplied by K, but this was being multiplied by 2, and this was being multiplied by 4, no. These two figures are not similar. Okay? All right, a couple more problems here. So this one says, how does this definition help you find the error in Mason's thinking in conjecture 1? So let's go back to Mason's thinking in conjecture 1. So we can clearly see that to get from here to here, that whatever that is not the same as from here to here, right? Because it almost looks like, let's just say, if this was 2 and then this is 3, if this is 2, then this almost looks like it's 5. So that factor is different. The scale factor from here to here and from AB to QR is very different, right? Okay. So how does this definition help confirm Mia's thinking about conjecture 2? So it helps Mia's because if we think about, where are we? Equilateral triangles. So remember the 2 criteria. Number 1, the angles are congruent. Are the corresponding angles congruent for these 2 triangles? And you're like, yes, all the angles are congruent. Okay, good. And then you'd say the sides. Okay, but one of the things you know about an equilateral triangle is they're all these sides are all the same. So I'm just going to pretend that this is X, right? And this is some other number Y. So when you're checking the proportion, you're going from corresponding side to corresponding side. So some people do division, some people do multiplication. I'm going to use division here just so it makes sense. So I'm going to take Y and divide it by X because those match. Those correspond. Then I'm going to take this Y and divide it by X. And then I'm going to take this Y and divide it by X. Do you see how these 3 all are the same ratio? That means the sides are in proportion. So if this guy was like, say, 5 and this was 10, these 2 aren't in proportion. But because they're all the same, Y over X, Y over X, Y over X, it does work because these are equilateral triangles, right? All right, let's move forward. Okay, number 9. It says, how might this definition help you think about other 3 conjectures? All isosceles triangles are similar. So when we were looking at them for these 2, here, all isosceles triangles are similar. We didn't have the angles being congruent. So this is where they failed. So let me put a little like, this is where we failed because the angles weren't congruent. The rhombuses, the sides were congruent, but again, I mean, the sides were proportional, but here again, the angles weren't congruent. So again, this is where we failed. And the reason why the squares one worked is because the 2 criteria, number one, angles are congruent and sides are proportional. They both worked. So go back over here. If you look at our work over here together, here we had, here we did not have angles being congruent because here, look at this angle versus this angle. Those 2 angles don't look anything alike. Same thing goes here. Look, see, that's a right angle. That's not a right angle. But for this third one, we had both proportional side and congruent angles. And I just realized this should have been 2 marks instead of 1 because that one was 1, so it couldn't be. All right, let's continue on. It says, from our work with rectangles, it's obvious that knowing that all rectangles have 4 right angles, for example, A for quadrilaterals, is not enough to claim that all rectangles are similar. What about triangles? In general, are 2 triangles similar if all 3 pairs of corresponding angles being congruent? So explain why the following conjecture is true. 2 triangles are similar if their corresponding angles are congruent. So let's do this. So if we say this guy is congruent to this guy, right? And this guy is congruent to this guy, and angle C is congruent to angle F, okay? And so maybe I just draw that in there. Oh, that looks a little bit off. Hold on. You know what I'll do? I'll just copy it. That's what I'll do. Okay. I just figured out how to hack this. So I'm going to copy this, right? And then I'm going to, this is basically what I'm going to do. I'm going to take him. I'm going to translate. Oops. I want to undo that. Oops. Redo. Okay. I want to take him and I want to, like, let's make him bigger so I can just translate him. Actually, I can't do that, huh? Sorry. So I want to take him and I want to line him up over here. That looks pretty good. Okay. So here I have, this is going to be C prime. Oops. This is going to be C prime and B prime. And what I'm going to do is I'm just going to dilate this triangle, right? I'm going to dilate that triangle so that C prime lines up to F and B prime lines up to E. Okay, so that's what I'm going to do. I'm going to take this guy. Oops. Okay, and I'm first going to line them up over here. This is not kind of how you would do it in the dilation world, but it's going to work for us just so that you can see what I'm talking about. And if you notice, that's exactly what happens. Look, he just moved all the way over and we get this line, right? So there you go. This is why it's true. Mia thinks the following conjecture is true. She calls AA similarity for triangles. What do you think? What do you think? Is it true? Two triangles are similar if two pairs of corresponding angles are congruent. So over here, we had all angles being congruent. And over here, we have two. Now, why would she do that? Why would she only use two of them? Why wouldn't she use the third one? Okay, so if you put this in the comment section, if you can come up with a reason of how you know that we only need two pairs, if you think about it, it makes sense, then that's extra credit for you. Or if you want, you can also put it, no, we'll put it in the comments. Okay. Number 12, it says, using the diagram given in problem 10, how might you modify your proof? Triangle ABC is similar to triangle DEF if you are given the following information about two triangles. Angle A is congruent to angle D. So the very first thing I'm going to do is I'm going to draw a picture. So I'm going to draw these two triangles and I'm going to try to make them look similar-ish just in case they are because my brain. So there goes that. And it says ABC. Oops. Okay. So that's ABC. This is DEF. Remember, order matters here. According to this, A matches with D because they're both first. B matches with E, and similarly, C matches with F, right? Okay, it says angle A is congruent to angle D. So we're trying to prove that they're similar. DE is K. DE, this is K, times AB. K times AB. So I'm going to make AB X. So this is KX. And DF is K times AC. So I'm just going to make this Y. So that's KY. And that is DE over AB. So DE, which is KX, over AB, which is X, equals to DF, which is KY, over AC, which is Y. Right, and if you notice, these X's cancel and the Y's cancel, so we get K equals to K, which makes sense, right? So it says, using the diagram, how might you modify your proof that these two are similar? So number one, we have, okay, sorry. Number one, so number one, you're like, oh, Miss Johnson, look, we so far have two sides that are proportional, two sets of sides that are proportional. good, right? So let's see. What am I doing here? So using the diagram given in problem 10. Oh, I was supposed to use the diagram in 10. Okay, it doesn't matter because it's kind of similar. How might you modify your proof that these two triangles are similar if you are given the information? Okay, so if I was given that this is similar to this, and we got proportional sides here, right? We know that since these two angles are congruent, right? And we know that these two sides are proportional to these two sides. What else would we need to say in order to prove that these two triangles are congruent? Similarly, what else would you need here? So this is where I'm going to leave you so that we can talk about this during class, so that you can see what we are working on. So I want you to try this. And while you're doing that, I'm going to go over takeaways really quick, just so that you guys can see what else we are working with in terms of that. So this first one says, to prove that two polygons are similar, right? To prove that two polygons are similar, we need to show that all corresponding sides are congruent and that all pairs of sides are proportional. However, there's if the polygons are triangles, we can show this using less information by using these three theorems. Okay, so here's the theorems. It's AA, triangle similarity. It's SSS, triangle similarity, and SAS, triangle similarity. So these are shortcuts, meaning you, instead of proving all sides are proportional and all sets of angles are congruent, here you only have to use AA. Here you would only have to prove that the three sides of the three sets of sides are proportional. And here you would have to do two sides and one included angle. Two sets of sides are proportional, and one is the included angle is congruent, right? So that should kind of tell you about this one that we were doing right here. If you look, we have side, and then the angle included. So this is going to be SAS, right? Okay, what else do I have for you for takeaways? It says, reflecting on the work with triangle similarity theorems, I learned or was reminded of the following insights about the proof process. So just remember that proofs based on transformations often require nothing that other than what is desired to be proved is impossible, since it would contradict some of the given information. So when you're looking at these things, just keep that in mind. Okay. So in terms of English, right? English for similar, it just means that they have some stuff in common. Like you and your classmate might have this class in common, right? But similar for math, it means two figures that can be carried onto the other figure by using translations, rotations, dilations, and reflections. In an alternative definition, similarity, and then this is the most important one that I really will like you to do, is corresponding angles are congruent and corresponding sides are proportional. Okay, so keep that in mind because that's going to be the most important part. Okay, make sure you read our lesson summary because that's going to help you understand and summarize all those things. Go ahead and practice using your exit ticket and your ready, set, go. Come with questions tomorrow so that we can go over what we need to go over. Thanks and have a great day. Bye.